We're going to start this lesson differently, with your eyes closed. Now, picture a dinosaur, any dinosaur. Start to paint the scene around them. What kinds of plants do you see? What does the ground look like? Do you see any mountains or clouds? What else might you throw into that view? A distant volcano spewing some smoke into the sky? A steamy sunset? Maybe a distant lakeshore? From what we know, dinosaurs did live in places like the ones that most people imagine when they try to situate them all those millions of years ago. But dinosaurs were found everywhere. No corner of the globe was free of the reign of Dinosauria, from equatorial islands to the highest latitudes on Earth, way up or down at the North and South poles. Right about now, I'm picturing you doing a skeptical double take. Wait a minute, did Kristi really just say that dinosaurs lived at the South Pole? That desolate, snow and ice covered no man's land? How is that possible? Could dinosaurs have thrived in such frigid climates? In this lesson, I'd like to share the story of the dinosaurs that conquered the cold. These are the polar dinosaurs. Let's start by orienting ourselves geographically and ecologically. In our modern world, we have two poles. Technically speaking, the North Pole region is that area of the Earth north of 60 degrees latitude, and the South Pole region is that area south of the 60-degree mark. The modern-day North Polar region we call the Arctic, and it's basically a frozen ocean surrounded by land. The South Polar region, on the other hand, we call the Antarctic, and it's a giant landmass surrounded by oceans. The Antarctic is generally colder than the Arctic. Both poles experience less intense solar radiation than the rest of the globe. They're heavily glaciated with year-round permanent ice, and they exhibit extreme variations in seasonal daylight. During the wintertime, each pole experiences 24 hours of darkness, and in the summers, each pole has 24 hours of daylight. Today, the biggest land vertebrates in the Arctic are polar bears, and in the Antarctic, penguins. Both are warm-blooded or endothermic animals. I don't think anyone has ever seen a cold-blooded land animal like a snake or a frog at either modern pole. It seems that being warm-blooded might be a prerequisite for survival at the polar regions of the Earth, at least in Earth's current configuration. But what about polar environments way back in the Mesozoic era when dinosaurs ruled the Earth? We can still define the polar regions using that same 60 degrees north or south latitudinal boundary. Back then, before the continents began to rift, both of these polar regions included significant land masses. But since the Mesozoic was warmer overall than our modern world, the poles lacked permanent ice caps. This is why we see much higher sea levels and shallow continental oceans during the Mesozoic. Without polar ice, all that extra water in the system had to go somewhere. So why not inland? But even though the Earth was warmer during the Mesozoic, these polar regions still experienced less solar radiation overall and were relatively cool. Just as in the modern world, there would have been extreme variations in seasonal light, 24 hours of darkness in the winter and 24 hours of sunlight in the summer. How do we figure out what the air temperature was over 66 million years ago? It turns out that fossilized leaves provide one way to determine that sort of detail. Scientists have taken a look at modern ecosystems and realized that the shapes of leaves provide clues to ambient temperature. In places where temperatures are pretty warm, leaves tend to have very smooth margins because they don't need as much surface area to have efficient photosynthesis. In cooler climates, leaf margins become serrated and rough, increasing surface area for photosynthesis. This relationship is really well established in modern ecosystems, which provides a convenient jumping-off point for interpreting temperatures in the fossil record. We can study the margins of preserved leaves in different places and estimate temperatures from there. These types of studies have revealed that mean annual temperatures at the Cretaceous North Pole ranged from about 2 to 13 degrees Celsius. That's about 36 to 55 degrees Fahrenheit. At the Cretaceous South Pole, the temperatures range from about -6 to 5 degrees Celsius, or about 28 degrees Fahrenheit to 41 degrees Fahrenheit. So just like in the modern world, the South Pole was, on average, a little bit colder than the North Pole. How do these annual temperatures compare to modern environments? Here are a few comparisons. The average annual temperature in Portland, Oregon is about 12 degrees Celsius. In Calgary, Alberta, 4 degrees Celsius. In Fairbanks, Alaska, -3 degrees Celsius. In my hometown of St. Paul, Minnesota, 7 degrees Celsius, about 44 degrees Fahrenheit. So with continental land masses at the poles, no permanent polar ice caps, but cold, snowy winters, wildly variable daylight, and relatively cool mean annual temperatures, how were dinosaurs able to live at the poles? Let's turn first to the North Polar dinosaurs, known from the North Slope of Alaska. So far, paleontologists have been able to identify a diversity of these dinosaurs on the basis of partial skeletons, isolated bones and teeth, and even footprint fossils. At least 12 different types of dinosaurs have already been discovered, all living in the late Cretaceous between about 75 and 70 million years ago. All of these dinosaur species have also been discovered at lower latitudes in western North America. The most common North Polar dinosaur is the duck-billed hadrosaur, Edmontosaurus. It weighed between 4 and 5 tons and is one of the largest known hadrosaurs from North America. A ceratopsian called Pachyrhinosaurus is also well known from the North Slope. Pachyrhinosaurus didn't have the nose horns typical of other ceratopsians. Instead, they sported massive, flattened rugose bosses, a large one over the nose and a smaller pair over each eye. Their frills were also decorated with unusual little flattened horns that pointed forward and down from the top edge of the frill. These dinosaurs also exhibited both a sharp, pointed beak and a thick row of cheek teeth, great for grinding down tough plant material. A smaller-bodied herbivorous ornithopod called Thescelosaurus also lived at the top of the world. These little dinos were bipedal and probably only a few meters long from head to tail. It would have browsed on vegetation low to the ground and used its little beak to selectively choose its food. Of course, there were plenty of carnivorous theropods in the mix as well, ready to make an easy meal of one of these herbivores. Theropods include the large-bodied T-Rex-like Albertosaurus and a few smaller species that may have been feathered, like Troodon, Dromaeosaurus, and Sornitholestes. Though pretty rare in the lower latitudes, Troodon is much more common up north. Data suggests that the Troodon species found in Alaska are larger than the species known from places like Montana and Alberta, perhaps the result of an evolutionary process called Bergmann's rule, which states that larger species are found in colder environments. There's even evidence of a diving bird known as Hesperornis, known from the North Slope fossil sites. Down in the South Polar regions of the world, we see a pattern. Way back then, there were 2 modern landmasses that were tucked below the 60 degrees south latitudinal barrier. The huge continent of Antarctica was below that line, as was the southern part of Australia, whose location was about 2,000 miles further south than its present-day location. Australia is known for small-bodied ornithischian dinosaurs, as well as small, fleet-footed, turkey-sized little herbivores like Liaonosaura and Quantosaurus. Sauropods and ankylosaurs also lived in polar Australia, as did a diverse array of theropods, from carnosaurs to dromaeosaurs and ornithomimosaurs. Farther south, in the transantarctic mountains, records of dinosaurs include even older fossil records, with prosauropods and theropods like Cryolophosaurus, known from the Jurassic period. This dinosaur is one of my favorites. It would have been about 20 feet long and weighed about 1,000 pounds, which ranks it as one of the largest theropods known from this early Jurassic time period. Cryolophosaurus, whose name means frozen-crested lizard, sported a distinctive head crest that is sometimes compared to an Elvis-style pompadour made of an upward curve of its forehead bones. The crest is relatively thin and delicate, prompting the hypothesis that it may have been used in intra-species recognition and sexual display. In other words, in both north and south polar environments, dinosaurs big and small, herbivore and carnivore, four-legged and two-legged, all seem to survive with no problem. Although this diversity might seem pretty high, especially for living at these latitudes, is actually relatively small compared to contemporary dinosaur ecosystems known from lower latitudes. The pattern of reduced biodiversity with increasing latitude is a trend that is also observed in modern ecosystems and may not just reflect taphonomic bias in the fossil record of polar dinosaurs. How in the world did dinosaurs cope with the cold? The presence of a diversity of dinosaurs inhabiting areas of the world with restricted daylight and relatively cold air temperatures begs a number of important questions. What did these dinosaurs do for food? Is there evidence for any kind of high latitude adaptation? When winter came, did dinosaurs migrate to warmer, lower latitude climates? Or were they able to contend with the cold, snow, and darkness? First of all, what was there for polar dinosaurs to eat? Our most abundant record on this question comes from the North Pole, where climatological data from fossil pollen, leaves, and preserved wood points to Cretaceous forests with a mixed canopy. Deciduous conifers, like modern-day larch trees, and regular conifers dominated the tree line, while the understory vegetation included a diversity of flowering plants, ferns, and cycads. When winter came, these plants would have gone dormant, dropping their leaves, slowing or stopping their growth, and reducing the amount of water in both branches and roots. This means that they wouldn't have been replenishing the necessary food resources for herbivorous dinosaurs during that cold, dark winter. If dinosaurs stuck around, they would have to significantly reduce their intake of plant material during the winter months. So, perhaps dinosaurs just took off, migrating to warmer climates when the cold and dark set in. Some scientists have suggested migration as the only plausible explanation for the presence of dinosaurs at the poles. For North Polar dinosaurs, this seems to be a realistic possibility because they lived in the contiguous North American landmass and could easily have headed south. Interestingly, scientists have used caribou as a modern analog to frame this hypothesis. In caribou, juveniles must reach at least 80% of adult length and close to 75% of adult body mass before they can undertake a migration from their northern home. When we zoom into the bones of preserved Edmontosaurus from the North Slope, a number of small juveniles have been recovered at only about 35% adult size and about 10% adult body mass. These juveniles were proportionally much smaller than juvenile caribou, making it seem unlikely that they would be able to undertake similar long-distance migrations at such small sizes. More recently, the discovery of just hatched baby dinosaurs in the Arctic suggests these dinosaurs could have stayed put as well. Such tiny babies just wouldn't have had the stamina to endure the long trek that a migration would require. At the South Pole, a northward migration would have been prohibited by significant marine barriers. Down south, it appears that dinosaurs would have had to endure the lengthy, dark winter. If dinosaurs stayed put, then they may have evolved specializations that supported this year-round lifestyle. Investigations of bone histology have provided possible evidence that some small-bodied Australian ornithomimosaurs may have hibernated during the winter. Regularly spaced growth rings point to annual or seasonal temporary pauses in active growth, and are similar to structures that occur in living mammals and reptiles that hibernate. Other sampled ornithopods don't preserve such growth rings, pointing to a different growth strategy in the two groups. It's important to note that growth rings do not necessarily indicate hibernation. They form in many living vertebrates due to other factors, including low food and resource availability, and simply as a result of evolution holding on to more ancestral types of growth patterns. No matter what, living in dens and hibernating would have only been options for the relatively small dinosaurs in these polar environments, It's unlikely that a 30-foot-long duck-billed dinosaur would have dug a hole in the ground to hibernate within. So far, there is no evidence of burrowing or denning in any polar dinosaur. The histological evidence is pretty inconclusive, but it does indicate that different polar dinosaurs grew differently, with some pausing throughout their life history while others grew continuously and rapidly. Are there any other possible adaptations for polar dinosaurs? In both the North and the South, we find evidence of specialization for seeing in the dark in two distantly related dinosaur groups. In the North, the small-bodied theropod Troodon appears to have been well-suited for life at high latitudes. At any latitude, Troodon is known for its relatively large eyes, but perhaps the large eyes proved adaptive for seeing in the low-light conditions of wintertime North Polar settings. Among living vertebrates, relatively large eyes are an adaptation for low-light living. Just think about any animal you can who's active at night. Owls, cats, lizards. In any of these nocturnal creatures, large eyes can take in more light and makes night vision a great tool for predators moving around in the dark. A similar pattern occurs in the small ornithopod called Lialnosaura, found in Australia, which has increased orbital diameters compared to closely related lower latitude dinosaurs. Might dinosaurs at the poles have had insulation in the form of fat or feathers? The fossil record has been slow to yield any secrets about these soft parts. Recently, a selection of fossilized feathers, discovered in Australia, indicates that some unknown species of dinosaurs inhabiting these polar environments did have feathery body coverings. The feathers weren't directly associated with bones, making a precise association impossible. But they included large feathers, about 1/2 inch long, that resemble flight feathers, alongside small fluffy feathers more similar to the downy feathers of living birds. They are hypothesized to belong to small, flightless theropods. You'll remember from our earlier lesson on the dinosaur-bird connection that the first feathers to evolve were fuzzy, downy feathers. These feathers couldn't have fueled flight in the ancient dinosaurs that wore them, but they would have been great at holding heat close to the body. Just think about how great it is to have a cozy down coat or down comforter in the deep, cold winters where we live today. Perhaps dinosaurs living in polar environments had their very own built-in down coats that kept them warm through the long nights. Could polar dinosaurs, pre-adapted for life in the dark and cold, have survived a little longer than other dinosaurs during the end Cretaceous extinction event? Could polar dinosaurs have been the last of the large-bodied dinosaurs? We'll dive into the details of what we call the KPG extinction in our next lesson. But one of the most significant drivers of the end of the dinosaurs was a post-impact interval of darkness, as clouds of dust and ash in the atmosphere blocked sunlight for a lengthy period of time. This would have resulted in a shutdown of photosynthesis and an eventual breakdown of the primary food chain. Though many of the localities that yield polar dinosaurs occur long before the extinction event, North Slope dinosaurs occur closer in time to the KPG. These types of polar dinosaurs would have already been adapted for scrounging around for food in the winter and surviving in environments that were dark for months out of every year. Perhaps they were able to stick around just a little longer than other dinosaurs at lower latitudes who were unaccustomed to these conditions. But in the end, even these cold-adapted creatures would have succumbed to the lengthy, severe conditions that characterized the KPG event. The takeaway? Polar dinosaurs existed, and did so throughout most of the age of dinosaurs in both north and south polar regions of the Earth. They seem to have had some adaptations for living in polar ecosystems year-round, and they don't seem to need to migrate over long continental distances to get to warmer climates during the winter months. Obviously, the question of whether dinosaurs survived polar climates has important links to the broader question of whether dinosaurs were warm-blooded or cold-blooded. You'll remember that endothermic animals are able to keep their own bodies warm when it's cold out just through the energy generated by their metabolism. Ectotherms, on the other hand, have to use the sun to keep them warm. Their metabolism isn't enough to cut it on a cold day. The presence of dinosaurs at both ends of the Earth are among the coolest evidence out there, no pun intended, for higher metabolic rates in dinosaurs, big and small. For us, it's time to leave these polar dinosaurs, breathing warm breath out of their noses, perhaps gazing up at the northern or southern lights, just as hot-blooded polar bears, penguins, and humans do in polar environments right now. Around 66 million years ago, however, maybe some of them looked up and saw something different in the sky. A huge asteroid that would mark the end of the world as they knew it. It's to that devastating event which we turn to next.